right, hi again, guys. Section 3 in our chapter 10 is all about using chords. So let's jump in. The first thing we're going to start with is a theorem that says if a diameter or a radius of a circle is perpendicular to a chord, then it bisects the chord and its arc. So what that means is if this diameter, EG, or even just the radius PG, is perpendicular to this chord FD, which we see here, then what I know from this theorem is that FH is congruent to HD because this chord has been bisected. But also when it says its arc, it means this arc that is, cut off of the circle when you drew in that chord. So arc FD is also bisected, which means FG is congruent to GD. All right, so if you want like an easy way to remember it, just if the radius, and we know that that means also the diameter, is perpendicular to the chord, then it bisects the chord. And you can always replace the chord with arc if that's what you're looking for. The converse of this theorem is also true. Now remember, most theorems, the converse is not true, but this one it is, which is kind of cool. And it says that if a diameter or a radius bisects a chord, then it is perpendicular to the chord. So if instead you knew that this chord had been bisected by a radius or even the diameter, then that would be enough to be able to say that this is actually perpendicular to the radius or diameter. And so just kind of writing the converse of this if-then statement, if the radius bisects the chord, then it is perpendicular to the chord. All right, so let's see. The next theorem is if one chord of a circle is perpendicular bisector of another chord, then the first chord is a diameter. So this is really the converse of the perpendicular chord bisector theorem in its true sense. Yeah, so let's just go take a look at how this information is going to be useful. So here's our diagram. It looks very similar to what we had in the last picture, but it's telling us that FD is perpendicular to GE, so that's why that marking is there. FD is 12, so this length right here, this whole chord is 12, and the radius is 10, so EP or PG are both 10. So let's just put a 10 here and we'll call that 12. That's the information that we have. They're asking us to figure out pH, and this is technically the distance that the chord is away from the center of the circle. We know its distance because it's measured along a perpendicular. So how are we going to figure that out? You might be thinking, oh, well, if I know that PG is 10, if I can figure out HG, I can just subtract that. And you're right, but we don't really have an easy way to figure out HG. Instead, what we might want to do is be clever here and think about drawing in this radius. Because remember, all the radii in this circle are all congruent to each other. So I know it's also 10. Okay, that's great. What we created was a right triangle, and we have the hypotenuse. So if we can figure out FH, then I can use Pythagorean theorem and figure out pH. And this is where our theorem that we just talked about on the previous slide helps us out. Because this is perpendicular to the chord, I know that this chord has been bisected. So if I take 12 and divide it by 2, I get 6. And now I look at this is a 6, if you know your triples, 6, 8, 10 triangle, and then pH is 8. If you don't remember your triples, you can just plug it into the Pythagorean theorem and solve it. All right, so what we're really going to be working on here is looking for, how can we utilize these right triangles to help us solve for missing pieces? And it all comes down to the fact that this is perpendicular and then the chord is bisected, and if the chord is bisected, then this is perpendicular. All right, let's see the next one. It says find the following values. All right, so let's look at what's in our diagram. We have this perpendicular symbol. Looks like NK is 7, and each of these arcs have an expression in terms of x. So the first question is asking us what is the length of HK, which is this entire chord. So what is that? Hopefully you recognize that if it's perpendicular to the chord, it has bisected the chord. So if this is 7, that's 7, and so then the whole chord is 14. Now the next question looks very similar, only this one has an arc over it. So it's actually asking us to figure out what is the measure of arc HK. So we want to know what is the measure of this whole arc right here. Okay, so what you're going to have to do is set up an equation to solve for x. And that equation is going to come from the fact that this arc has been bisected. So what is the equation that you're going to set up? Don't solve it, just what's the equation? Hopefully you did 11x equals 70 plus x. And now we can solve for x. What did you guys get for x? So when I solve for x, I got x is 7. And now I can figure out what HK is by plugging in 7 for x. And I can do it here or I can do it there. It really doesn't matter. I'm going to plug it into the easy one. 11 times x is 77. But that's not the final answer, right? Because that's only HJ. We want arc HK. So I know that this arc has been bisected, so I can just take that 77 and multiply by 2, or add 77 plus 77, either way, and I get 154 degrees. Okay? All right. Let's see. The next theorem we have says that in the same or congruent circles, two chords are congruent if and only if they are equidistant from the center. So that means that if I want to say that chord AB is congruent to chord CD, I need to know that these little segments, these represent the distance, right? The chord is away from the center. I need to know that they're the same. But I also can go the other way. If I know that these distances or lengths are the same, then I know that the chords are congruent. That's the whole if and only if. It goes both ways. Okay, so let's see how this can help us. In the diagram, we have AB is equal to CD, which is equal to 16. PT is 2x, and PS is 5x minus 9. They want us to find the radius of circle P. Now, I can draw the radius anywhere I want, but I'm going to draw it so it's useful. I'm going to draw it to make a right triangle. So this is the length that I'm looking for. Now, this is 2x. That doesn't really help us, does it? But they told us that these chords are 16. And because this is perpendicular to the chord, I know it bisects it. So each of these are going to be 8. So now I have 8 and R. All I have to do is figure out what this length is, and I can solve for R. So this is where the equidistant chord theorem comes in. Because they said that these chords are equal, that means that the chords are congruent. And if the chords are congruent, that means that they're the same distance away from the center. So PT is equal to PS. So now I can set up an equation and solve for x. And I get x is 3. All right, fantastic. So plug 3 in here and we'll get PT is 6. So now I know that this is 6, this is 8. You can quickly figure out R is 10, or if you needed to use Pythagorean theorem, that's what it would look like. Okay, really quickly, I'm just going to show one other thing. I know it's not in your notes, and that's fine. Eventually, we had a plan that we were going to extend Chapter 10 a little bit and do more, but of course, with the situation that we're living in right now, we're not actually going to do that, but I wanted to record the video anyway for future use. So if you're interested, take a look at the next slide as I go through it. If not, you guys are done. All right, here we go. So the theorem, in the same or congruent circles, two minor arcs are congruent if and only if their corresponding chords are congruent. So here we go. The corresponding chords and arcs that they're talking about. So if you have these two chords, the arcs that they cut off are what they're talking about. So if the chords are congruent, then the arcs are congruent. Okay, so if the arcs are congruent, then the chords are congruent. It goes both ways, right? If and only if. So this is actually really interesting because if we take what we learned from the last section about how central angles and arcs relate to each other, you can kind of put it all in one thing. So you can say congruent chords imply congruent arcs, which also imply congruent central angles. And you can go back and forth, pick whichever two you want to talk about to be able to prove something's congruent. So for example, if these chords are congruent, then I can say these arcs are congruent. Or if these angles are congruent, then the arcs are congruent. Or if these arcs are congruent, then the chords are congruent. Or I can say if the arcs are congruent, then the angles are congruent. You see the idea. You can go back and forth, and whichever pair that you want to say that you know are congruent, that implies another pair is also congruent. All right, that was all I wanted to show. Okay, bye.